In the last video, we talked about the distance being the total length traveled going between 2 points. And now, then that seems simple enough. And so what I want to do now is talk about distance and defining it in a much more complicated way. And so you might ask, why would you want to do such a thing? And the reason is we're going to use this method, which is definitely more complicated, later on, and we'll have to use it to be able to explain something that is pretty subtle. If at that time both the method is complicated and the idea is subtle, a lot of students get lost. So what I'd like to do is illustrate this particular method of thinking about distance, think about this method and applying it to something that's very simple, like distance, gives us an idea to explore and get comfortable with this method of doing things, and then later when we use it for something subtle, it should be easier. Okay, so I'm going to find some position here, call S sub I, and some position final that I call S sub F. And so you might think of these as some position as the result of two position vectors, R sub I and R sub F, from some coordinate system in the positive X, positive Y axis. These are 2 points from a position function in time, evaluated at 2 times initial time and some final time. Okay, so So that's how we think about it, but let's clear off this other stuff and just think about these initial and final positions, this dot, initial, this dot. And so let's say this path went to the right 6 meters and then up 4 meters. And so we would say then that the distance, I'll call the distance S here. We'll call this the distance S, and we know that that is 10 meters, the total distance traveled. Fine. Okay. So what I want to do is introduce a new friend. This is my nanobot, and my nanobot is very, very small, almost the size of an individual atom, nanometers in size. So this is my little microscopic robot. And so nanobot, what he does is he can travel along this path and measure the distance for us. So how nanobot does that is nanobot takes very, very small steps. Each step is a straight line, but he keeps track of how far but he knows exactly how far each step is, keeps track of all the steps necessary, the steps necessary to go the entire path, and then adds them all up to get the distance. So in this case, nanobot would go along this path, taking these very, very small nanometer-sized steps, but nanobot would be able to keep track of all of the size of each one and how many they all are, and at the end calculate them all up and tell us the total distance was 10 meters. So this allows me a different way to define my distance. Instead of just the total length traveled, my distance then is the sum of all the very, very small steps. I'll just use one very, but emphasis, the very small steps taken along the path from S initial to S final. So my total distance is the sum of all the very small steps my nanobot took from going along the path from the initial position to the final position. And so here's what is neat, is that I can write that sentence in a mathematical form. I have a notation that means exactly that sentence, which is why I wanted to go this direction. So my distance S, and in this notation is curly line there, then S initial, S final. And so what this, if you haven't seen this notation before, this might seem very strange, but all this notation means is exactly this sentence, and I'm going to rewrite it. This orange squiggly line means sum of all the, and then this ds means very small steps taken along the path, and this is here, from S initial to S final. And so I will make a one important point here, is this quantity right here, this d is not d times s. It's a single thing, combined ds, and what that means is the very small steps taken. It's one of the very small steps taken along the path. So the very, very small steps, each one I'm going to call ds. And if I sum up all the very small steps taken along the path, I get the total distance. Okay. And so I think that would make sense, though at this point it may not be obvious why we'd want to make it that complicated, but we will need this part later on. But let's do another example here. In this case, I have 2 points. Here's an initial, and here's a final, and they lie on opposite sides of a circle, and the path taken to get from one to the other lies on a circle with radius r. Okay, so how does this work? And it's the same thing now. I'm going to take my nanobot here, starts at SI, and walks, taking very, very small steps all along this path. And it's at this point where the idea of taking these very, very small steps makes a difference. I mean, before, he was just going in a straight line, and so it was going 6 meters and then 4 meters. But here, it's curved every time. And so how can you measure that by taking steps? That's why the nanobot was important. If I blow up this curve here, I have this slight curve, and then it gets if I look at it, it's less curved, and then if I go really in, just a microscopic picture of one part on the curve, at that point it looks like a straight line. And that's what the nanobot sees at each step. So the nanobot takes steps that are so small that at each step the curve looks exactly like a straight line. Therefore, the nanobot can take a step in a straight line and still stay on the curve because the steps are so small. And so the nanobot goes, it takes these really, really small steps where every step is in a straight line, but every step is so small it stays on the curve until it gets finally to the end, and then the nanobot can sum up how long was each step and how many steps were there, and can come up with the final distance. And in this case, the distance was pi times r. Let's say the r was 10 meters, and so the nanobot says the distance was 31.4 meters to 3 significant figures was the distance traveled from the SI to SF. And so let's take a look at this. Again, the distance here is the total length traveled, which in this case was solved by looking at each by nanobot taking very small steps, each of length ds, and then summing them all up, which is what that notation means, and then it went from some initial position to some final position. Okay, so this is a process that I hopefully conceptually makes some sense, and that will be at least familiar when we use it later on to look at more subtle concepts. The other useful thing about this, I will say, is it allows us to define displacement and distance in such different ways. Hopefully you will never be confused by them again. Remember, the displacement was a vector where that vector between two vectors from a position function separated by 2 points in time, some final vector minus some initial vector. Well, assuming those vectors point to positions S initial and S final, then the distance is then defined by this notation from S initial to S final of these very small steps ds. And hopefully this is different enough that you should be able to keep these two concepts separate.